Okay, so guys, we're going to be going over the basics of waves. I'm going to try to keep this real concise. All right, here's a wave. First term to know, wavelength. If you look it up in a dictionary, the definition that's most commonly given for wavelength is peak to peak or trough to trough, or crest to crest. That would be wavelength right there. The symbol for wavelength is lambda, or you could say trough to trough. That would be wavelength right there. The definition I prefer is from one point on the wave to the next identical point. So like, look, boom, where's the next identical point? There. That would be wavelength. Or you could go, there to there. From one point on the wave to the next identical point. And then what's the unit for wavelength going to be? It's a length. We measure it in meters. Okay, next term, frequency. Now guys, frequency, it's a term that we've used before. It's not just for waves. Frequency, I mean, the definition is right there in the word. How frequently does Spaldo eat at In-N-Out Burger? I'll tell you. 3 times per month. Would that be a frequency? Yeah, frequency is anything per time. How often does something happen? Now in physics, are we going to be per month or per week, per day, per hour, or per second? What's our unit for time in physics? Second. So the unit for frequency is called the hertz. And a hertz, so we abbreviate it Hz, and a hertz is literally 1 over a second. It means per second. So what if I told you that this wave right here had a frequency of 500 hertz? What would 500 hertz mean? 500 waves per second. Like if you put your finger right there, how many waves would pass your finger in 1 second? 500, if the frequency were 500 hertz. Okay, next term, velocity. Now come down here. I call this the wave equation. The velocity of a wave can be found by multiplying the wavelength by the frequency. And let's just look at why that works. It's pretty simple. Velocity is wavelength times frequency. What's wavelength measured in? Meters. What's frequency measured in? 1 over second, which is called the hertz. What does that come out as? Meters per second, which is velocity. Wavelength times frequency is velocity. All right, next term, period. Now, period is very closely related to what? To frequency. They're very, very closely related. In fact, they're the inverse of each other. So for starters, what is period? Period, and we've talked about this before. When did we see period before? It's not just a term for waves. It's with a pendulum, right? What's the period of a pendulum? The time for one complete there, back. And by the way, dudes, for the AP test, you should have that memorized. There's an equation for the period of a pendulum. Careful, Spaldo. You're getting off topic here, but this is important. This is for a what? This equation right here is for a what? Pendulum. What's the other thing that has a period? Mass on a spring, going doing, 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 doing. How do you calculate the period for mass on a spring? 2 pi m over k. You should have those memorized. Okay, so back to waves. What do we mean by the period of a wave? Well, what is period? Period, whether you're talking about a pendulum, mass on a spring, or a wave, period is the time for whatever it is you're talking about, right? So here it would be the time for one complete wave. It's the time for one complete cycle. What are we going to be measuring period in? Seconds, right? It's going to be measured in seconds. Now, what's the relationship between period and frequency? Okay, and again, this is not just for waves. This is for anything with period and frequency. What's the relationship between period and frequency? They are the inverse of each other. So frequency is 1 over period, or period's 1 over frequency. Let me give you an example. Ready? I'm going to clap my hands twice per second. Okay, look. What's the frequency of that? I'm clapping my hands twice per second. The frequency would be what? 2 hertz, right? what would be the time for one clap? Half a second, right? That's the period. Plug that in there, you get 1/2 for the period. Frequency and period are the inverse of each other. All right, amplitude. Amplitude is the maximum distance off the equilibrium position. The equilibrium position would be like if this wave were to die, like imagine it's an ocean wave, like a wave traveling across the surface of the ocean. If this wave died, where would it die to? It would die to the equilibrium. The amplitude is the maximum distance off that equilibrium. All right, now, key idea, and we're going to come back to this in a moment. The velocity of a wave remains constant. It remains constant for a given medium. If the medium changes, like let's say you have a light wave, right? Light is wave-like. What if light goes from air to water? Would that be a change of medium? Yeah, and then the velocity changes. But if you're talking about light in air, it doesn't matter if you're talking about red light, blue light, green light. All light travels at the same speed in a given medium. Okay? All right. Next page. Okay, wave basics. The two major types of waves. This is I've seen this on the AP test, like on the multiple choice. They like to. Who's seen this on the multiple choice? Transverse and longitudinal. They like to ask this. Real simple. Okay. Uh-oh, my projector's. Oh man. Am I recording here? Okay, the two major types of waves. Transverse waves. A transverse wave, so I'm going to talk about this definition here in a moment. But guys, a transverse wave is what most people think of when you think of a wave. When you think of a wave, very rarely or probably never would you ever think of a longitudinal wave. So transverse waves, it's what most people think of. So like examples, a ripple in water. You throw a pebble into some water, you're going to create a transverse wave. Or like if you create a wave on a string, like you hold a string, you start shaking it, that's a transverse wave. So the definition of a transverse wave is that a point on the wave travels perpendicular to the velocity of the wave. Like what? Hold on, it's real simple. Guys, look, here's a transverse wave like this. But let's say you're talking about a wave traveling across the surface of water. Like you just threw a brick into a pool, okay? And you have a little toy boat. There's a little toy boat floating in the water. Okay, so you threw a rock. So here's your boat right there. There's the boat. So you throw a rock into the pool. The wave is moving like that. That's the velocity of the wave. When that wave hits the toy boat, is the toy boat going to be like boom, like that? What's the toy boat going to be doing? The toy boat is going to bob up and down, right? A point on the wave moves perpendicular to the velocity of a wave. Just think about a rope. If you put a wave in a rope, the velocity of the wave is moving down the rope. But what's a point on the wave doing? Moving perpendicular to that. That's the definition. Now, what travels transverse? Ripple in water, light, all electromagnetic radiation like X-rays, gamma rays, radio waves, infrared, ultraviolet, all forms of electromagnetic radiation are transverse. Now, longitudinal, there's really one key example of longitudinal waves, and that is sound, or a wave pulse traveling down a slinky. For a longitudinal wave, so imagine this. Imagine I had a slinky attached to the wall, and I pull the slinky straight back, right? Not up and down. I pull the slinky straight back, let it go. There'd be a wave pulse that shot down the slinky, right? So see right here? So the velocity of the wave is down the slinky. If you look at a point on the wave, which way is a point on the wave moving? Parallel. Does that make sense? So longitudinal waves, a point on the wave travels parallel to the velocity of the wave. The best example is sound. Sound is not transverse, it's longitudinal. Okay. Now, to the good stuff. Standing waves. Now, before we do standing waves, I want to show you a video on YouTube here so you can just see it. A standing wave is a wave that remains in a constant position. So check this out. Here's a standing wave. So see that? It looks like there's certain points on the wave that are not oscillating up and down. Okay, then we'll fast forward this. So you can see a standing wave can change. Is that vibrating faster or slower than the first? Slower. And then that's called the fundamental, right there where it ended. Okay, so let's look at my lecture. So a standing wave, it's a wave that remains in a constant position. Now the shape of the standing wave depends upon the frequency. So here we got this guy's hand. This guy's hand is going up and down, up and down, up and down, you know, creating this wave. So first off, I want to show you how to figure out the wavelength of these standing waves. So let's just say, for example, that from here, from the hand over to that hook, I'm going to give you a distance, 2 meters. Okay. What would be the wavelength of this first one? Oh, and let's go through the terms. Sorry, the terms. This is referred to as the first harmonic, also called the fundamental frequency. It's the first possible way that that string can vibrate. This would be called the second harmonic. It's the second possible way that that string can vibrate. Hey, what happened to the frequency from the first harmonic to the second harmonic? Is the dude's hand going faster or slower? From the first harmonic to the second? Faster. Then this right here is the third harmonic. Okay, even faster. Guys, what's true about the velocity of the wave for all three of these? They're the same. The velocity of the wave depends upon the medium, which is the string here. It's the string. Is the string changing? No. So the velocity of the wave stays constant. See, I even put that up here? The velocity of the wave remains constant. So look, if the velocity is constant, if this is constant, then what must be the relationship between wavelength and frequency? As the frequency goes up, what's going to happen to the wavelength? It's going to go down, and vice versa. Okay? So what I got to show you is how to figure out the wavelengths. It's really easy. I'm telling you, dude, it's easy. So let's say from there to there is 2 meters, right? So let's figure out the wavelength for each of these. What's the wavelength here? What's the wavelength here? What's the wavelength here? All right, so how do you do this? Look, let's start with the easiest one, which is the middle. This is the easiest one, okay? What's the wavelength of that dude? It's got to be 2 meters. It's the given distance, right? Because remember, what's my favorite definition for wavelength? It's from one point on the wave to the next identical point. This would be one wavelength. Look, boom, boom. That's one complete wavelength. So the wavelength here is 2 meter. All right, let's go to the first one, the first harmonic. How could we get the wavelength for this one? Well, what's the 2 meter equal to? So the total distance here is 2 meters, but how many wavelengths is this? From there to there, is that a full wavelength? How many wavelengths is it? It's half of a wavelength. It's wavelength over 2. So what must the wavelength be equal to? 4 meters. You guys see what I did? You just got to think, like, what is a wave? A wave is like this. So look, this would be wavelength from there to there, or like from there to there. That is a full wavelength. What do we have in this situation here? We have exactly this, which is what? That's half of a wavelength. So the 2 meters, the whole distance, is equal to wavelength over 2. Okay? All right, let's do the last one. Let's get the wavelength for the last guy. Uh-oh, I didn't want to do that. Okay, let's do the wavelength. So this is 2 meters. Come on, Spaldo. Am I going too quick? 2 meters. All right. So what's the wavelength for this guy? Well, look, what's the 2 meters equal to for the third harmonic? How many wavelengths are from here to there? Let's see. We got 1, 1 wavelength to right there, and then what's that? Half. So this is equal to 1.5 wavelengths. So what's the wavelength going to be equal to? 2 meters over 1.5. So what's that? 2 divided by 1.5. 1.3 repeating. Okay? Does this make sense? Okay, so final thing, let's do a problem and then we're done. Okay, so here's a problem. Same diagram as before. You're given the fundamental frequency. What does the fundamental frequency refer to? It refers to the first possible vibration. So this baby right here is vibrating at 7 hertz, and then I give you the length of the string. From there to there is 1.5 meters. So what we're going to do is we're going to find the speed of the wave, the velocity. Then I want you to figure out what must be the frequency of the second harmonic, and then what must be the frequency of the third harmonic. So take 5 minutes. Made the diagram a little bigger. So the information we have is this. The fundamental frequency, so referring to this right here, the frequency of this guy is 7 hertz, and then the length of the string is 1.5 meters. So that is from here to there is 1.5 meters. So what we got to do to find the speed of the wave, the velocity of the wave, is we need to figure out the wavelength. What's the wavelength that corresponds to this first harmonic? Well, how do we do that? Well, so from here to there is 1.5 meters. So 1.5 meters is equal to what? Is it equal to a full wavelength? No. It's equal to what? Wavelength over 2. This is half of a wavelength. If you think about a wave, here's a wave like this. You know, we have from there to there, which is half of a wavelength. So what must this wavelength be equal to? 3 meters. Okay, so then we go to the wave equation. The wavelength there is 3 meters. So velocity equals wavelength times frequency. So we multiply these together. What's the velocity of the wave? 21. Oops, back to here. Whatever. This is 21 meters per second. And then, by the way, what's going to be the velocity of this wave? 21 meters per second. What's going to be the velocity of this wave? 21 meters per second, because the velocity of a wave is constant for a given medium. Okay, and the medium here is not changing. Okay, second question. What's the frequency of the second harmonic? All right, so we're focusing in on this second harmonic. First, let's find the wavelength. What's the wavelength there? So from there to there is 1.5 meters. Okay, so what's this wavelength equal to? It's 1.5 meters. We have a full wavelength there. So how do we find the frequency? Velocity is wavelength times frequency. Frequency is going to be velocity over wavelength. So that's 21 meters per second. They all travel at the same speed. The wavelength is 1.5. So that gives us a frequency of 14. Okay, so this is 14 hertz. And then the frequency of the third harmonic. So to find the frequency of this third harmonic, we first need the wavelength. Well, how do we get the wavelength? Well, 1.5 meters is the total distance. What's the 1.5 meters equal to? 1.5 meter. How many wavelengths are in here? 1.5 wavelength. That's a wavelength and a half. So the wavelength is equal to 1. This is 1 right there. So now what's the frequency? To get the frequency, you go velocity is wavelength over velocity is wavelength times frequency. So frequency is going to be velocity over wavelength. That's 21 meter per second over 1 meter. That gives 21 hertz.